Okay, in this recording we're going to look at the fundamental theorem of calculus. The fundamental theorem of calculus actually has two parts to it. In this recording we'll look at part 1, and the next recording we'll look at part 2. Now, remember we discussed the mean value theorem. The value f of c in the mean value theorem, or we actually found the average value of functions in the last recording. The average value of a function f on a of b is just the average height of that graph. Okay, so when f is greater than or equal to 0, the area of the rectangle is the area under the graph of f from a to b. So if I take f of c and I multiply by b minus a, I'll get the integral from a to b of f of x dx. Okay, so the mean value theorem for definite integrals, if f is continuous from a to b, then at some point c in a to b, f of c is 1 over b minus a times the integral of a to b of f of x dx. Okay, so at some point it takes on that mean value, or that average value. Now it did have to be continuous. Here's an example that shows you that it does not hold if it's not continuous. Here, this graph is discontinuous at 1, but the average value is 1/2. Notice, though, that this graph never takes on the value of 1/2. It has to be a continuous function. Okay? Now, this is equation 1 from this section. If we have a function capital F of x, and that capital F of x is the integral from a to x of f of t dt. Okay, so we've got the area that you see in blue here, the area from a to x of f of t dt. Okay, that is going to be capital F of x, and that is the area under the graph from a to x, where f is non-negative and x has to be bigger than a. Then the fundamental theorem of calculus part 1 says if f is continuous on a to b, then capital F of x is the integral from a to x, f of t dt is also continuous from a to b, and it's differentiable between a and b. Its derivative, f of x, the derivative is f of x. In other words, capital F prime of x is the derivative of the integral from a to x, f of t dt, which is actually just f of x. Notice what happened here is we took the upper limit of integration, which is the x, okay, and it's a variable. A is a constant, a number, and we just plugged x into f of t. Now this is very easy to apply. Here we have the integral from a to x of cosine t dt. Okay, so if we want to find dy dx, so if we want to take the integral, or the derivative of this integral, then that's what we get when we take x and we plug it in for t. So that is just cosine of x. That is going to be the derivative of this integral. Now, what you can think about here is when you're taking a derivative, and when you're doing an integral, you are actually taking an antiderivative. Remember, the integral symbol told us to find the most general antiderivative. Well, what we're doing here is we're doing opposites of each other. So if I take the derivative of an antiderivative, they are opposites of each other, and so that's why it ends up being just cosine x. Now, the x does have to be the upper limit of integration, okay? So, this, remember, is the opposite of the integral from 5 to x of 3t sine t dt. Okay? Now, once I do that, then I can just apply my rule. And so this is negative, and I just take this x. Okay, well first I didn't put my dy dx, so let me start over here. Dy dx is the negative, or opposite, of what I get when I plug in x. So that's the opposite of 3x sine x. Okay. Now notice it didn't matter what the lower limit was. Here it was a, here it was 5. That doesn't matter. You're taking an integral from some lower constant to x. Now the one thing you do have to be careful with, the fundamental theorem, is if you don't have x. If you have some upper limit that's not just x, maybe x squared, or any other composite function of x, what happens then is, since this is a composite, we have to do the chain rule. And so when I do dy dx here, I am going to take the x squared and plug it in for cosine. Okay, so I will have cosine of x squared, but I'll have to multiply by the derivative of x squared since it's a composite. Okay, anytime that this is not just x, we will have to use the chain rule. Of course, the derivative of x squared is 2x, and I'm going to put it in the front, so that's 2x cosine of x squared. Now, if you're just going to x, as we did here, you don't have to worry about that. You just plug the x into the formula. Plug the x into the formula. If it's x squared or anything other than just x, any composite will have to plug the x squared in, or whatever we have there, but then we'll also have to take the derivative of x squared. Now, this is the first part of the fundamental theorem. We will look at the second part of the fundamental theorem in the next recording.